Assalamualaikum and hi. My name is Nu'aini Adira binti Kamal Arifin and my method number is CE10049. So for this group project, I will present about the introduction, objective and the discussion. So first is for the introduction. The introduction for this group project is a computer program is started to operate when it is executed. Then it implies that the program is being started and programs executed by system and run by individuals when it is in use. Then a computer processor carries out an instruction. It does the tasks that are specified in the instruction. A file that includes a program is called an executable, and it has a specific type of file that can be run as a program in a computer. As an executable file, somehow the file name extensions in this operating system or Windows operating system such as .dat, .com or .exe. Then the system memory is used for execution of a program, and its memory contains a set of instructions, and the pointer receives a copy of the memory address, and it is where the first instruction is located. The address contained in the instruction pointer is sent by the CPU through the address bus to the memory. Then control bus receives a read signal from the CPU. So for this group assignment, we use Ride Simulator, which it is a graphical processor simulator and assembly code editor built for RISC-V instruction set architecture. It is suitable for teaching how assembly level code is executed on various micro architectures. Then RISC is used to explore concepts such as how machine code is executed on a variety of micro architecture. For example, is RB32IMC or RB6 for IMC base. So next, for the objective, first is to make the computer system efficient and convenient to use, and it used to shield users from the specifics of the hardware resource, to control a computer system resource. Then it used to monitor resource usage, grant resource requests, and resolve disputes arising from computing demands made by various applications and users. Last is to ensure efficient and equitable resource sharing between consumers and programmers. So next is for the simulation result and also the flowchart. I will pass to my group members.
Hi, my name is Chongshin Lee, matrix number CE10008. So I'm going to explain about the flowchart for our group project. So our group project simulation, first we have to start and then define the assembly code in brief. After assembly code is defined, we have to move to the process in device the instruction set code, and then we will move to the catch process. If the process is no error, then we will proceed to the catch process. If there is an error, then we will go back to define back the assembly code. After that, after the catch process, we will move to the output of data catch, size and instruction of catch. After that, we will move to the catch access and the status and plotting. So that the process will end. The detail of this project, my other group member will explain about it. And now I'm going to explain the simulation for our group project. So first this is the assembly code that we already defined. So now let me click run. So this simulation will keep running. For this process, it will take some time. So in order to save our time, I will directly click this. It will directly give the result. So here is the result, the console here. This is our result for our simulation. So for the editor tab, they have shown two two code segments. So we can use either assembly code or C code to do this project. So in our case, we are using the assembly code. So next we are going to move to the processor tab to see what will happen. So this is the processor tab. So this is the 5-stage RISC-V processor. So for this tab, this is to display the currently selected processor, and then as well as any additional information will relevant. It is relevant to this execution. So we can see here is the register, and then followed by the console, which is the output, and then the execution info, which is the statistic. And then we have the instruction memory. So for the register, this is the register. This is a list of all register of the processor that we use, and then the value can be edited through clicking on the value or clicking on the value of the given register. So we also can edit the register value in the register value that we editing will immediately reflected in the processor circuit. The most recently modified register is highlighted with a yellow background, which is here, as you can see here. So for the instruction memory at the right corner here is a view into the current program loaded in the simulator. So the BP is mean that the breakpoint, click to toggle, any breakpoint can be set in the editor tab will be reflected in here. For the PC is the address of the given instruction. And then for the stage is the list of the stage that is currently executing the given instruction. So last here is the instruction, which is the deassemble instruction. So lastly, in the output console here is any output through the echo print function will be displayed here, which is our here the result that we have run here will appear in here. So next for the cache process, my group member will explain more detail about this. Then now we will go to the memory tab. So for the memory tab here, this memory tab is provide a view into the entire address space of the processor. It navigating the memory. Navigating the memory can be done as scrolling the memory view like this. Then maybe we can go to the register. Go to register, we scroll the memory view to the value currently present in the selected register. Then if we go to the section, we'll scroll the memory view to the address of the given section value in memory. For example, the instruction memory segment, the statistic data segment. So furthermore, the custom address may be specified through this address option. So whenever the processor is reset or the memory written during the program execution will be reset to its initial state. So this is for the memory viewer and memory map. So that's all for my part. So for the next cache memory, my other group member will explain about it. Thank you.
Greetings to Puan Munira. I'm Hon, and now we will explain our derived instruction set code. So this code we using the assembly language. So it's about the implementation of the multiplication of two complex number, which is Z and W. So firstly we derive the data first. So we define our real part of Z, the imaginary part of Z, real part of W, and also the imaginary part of W in AA, BB, CC, and DB. So also we have to determine the string. So the string is actually the plus I multiply. So after this, we derive the main code from the data that we derived just now. We try to load the words into A0 to A3. So after this, we try to do the complex multiplication of the number A0 to A3 just now. After this, we also try to print the real and imaginary value in A0 by setting equal argument to 1, and also the delimiter string, the pointer in A0 by also setting the equal argument to 4. So after this part, iteration variable, and also to initialize the temporary product register to 0. And after this, we do the shifting by using the arithmetic right shift, and then we also move the final product to the result register. And then after this, we also derive the code that is to put the 4 input argument to and return address on the step point. So we also define some of the step point, which is the ABCD, the return address, and then we also have the temporary register 1 and 2. So after this part, finally we get into the operation of the multiplication of the two complex numbers. So since this is our formula, so we have to do it part by part. So firstly, we do the step 1, which is A times C. After this, we do the step of B times D multiply D. And then after this, we use the AC and BD, and then we have to subtract them. So after this part, we do the A multiply D part, and step I is B multiply C, and then after these two steps, we plus them together. So the final result, we reload the return address from the step, and then we also restore the step pointer. So that is all for the source code. Now we will do the explanation on the process of cache. So let us click to the cache window. So the rigs also includes the cache simulation, and then we have the L1 data cache and also the L1 instruction card. And now we will be looking at the L1 instruction card. So inside this instruction card, so let us run the simulation first. So we can see that the first one, we can see the cache configuration. So it is actually the sum of the parameter here. So the first one will be looking here is the 2n lines. So the lines is means the number of the cache line here, and then 2n ways. So the ways is actually the specification of the association of this code, and then 2n blocks. So the blocks is means the number of the blocks contained in each cache line. So the number of blocks here will be the size of the block that's used to choose a cache line block here. And then we have the placement policy for cache, and also the write hit and miss policy cache here. So after this, we look into the cache view. So this is our cache view here. So in this table, the color line is used to separate the cache line, and then we have the raw line is to separate the waste that add to the same catch line here. So the catch view column is defined as following, which is the first one. V here is actually our valid peaks. So valid peak is to determine whether data in the cache is accurate or not. So if it is accurate, for example, in the index 0 here, if the data is valid, so the valid peak is 1 here. And then for D is actually our dirty peak to determine whether the cache data is corrupt or not. For example, in the index 0, if it is not corrupted, so the dirty peak is 0 here. And this we have tag. So the tag is the cache where current tag. And we have the block 0, 1, 2, and 3 here is our cache data. So after this, at the same time here, we actually complete our simulation. And then after this, let us look into our catch access statistic and also their plotting. So in the plot configuration, we have the numerator, which is hits, and the denominator is the SS counter, and then we also enable the moving average in 50 cycle. And then for our statistic here, we have the size of the catch here is 4,869 bits. So what it means by that, by clicking the question mark here, we can see the catch sign. Here we have the valid bits is 32 of dirty bits, 0 of LRU bits, 736 of tag bits, and also 4,096 data bits. So total all we have 4,896 bits. And then by choosing the numerator and denominator, so we can see the ratio between any of them is plot here. So we can also look the moving average plot here. So it helps to determine when the heat range drastically varies during this simulation. So that is all for our simulation.
So as for the discussion, from this assignment we learned the structure and operation of the CPU, which how it was functioning for each CPU component. In computers, to execute a program is to run the program in the computer and by implication, to start it to run. In usage, people run programs and systems execute them, and systems execute the programs. Hence, we can see how the cycle of instructions being executed from the CPU. Programming a parallel high-performance application is generally more complicated than developing a comparable sequential code, as the pointer is a program counter. It used for the program flowing by the CPU. The default program flow also can be altered via branch instruction, and then we know the types of commands that a computer is capable of carrying out. The commands are by using operations in logic and arithmetic, which it is one of the methods for moving the data between the CPU and RAM memory, and from that we can see those instructions being executed from branch that alter the program flow, which the branch instructions execute will be conditional. So for the conclusion, I will pass to my group mates, which is Chong-Shin Lee, and this is all from me. Thank you.
So as a conclusion for our group project, so we have done complete our simulation using the RIPS simulator. So we're able to investigate notion of the computer architecture and organization in this project. So before we conducted our own equation in the coding, we learned the basic on how to derive the equation that contains the related operation of our equation. Then while we using the RIP simulator, we know how to assemble the language code to express the equation. So after that, we execute our equation by simulating using the RIP simulator and see if the output as predicted or not. So as the feature can be seen from this simulation result and supported by the explanation of the coding. So the structure of the flowchart in this project also stated a clear pathway of our system. So finally, we can conclude that our group project is a success. So that's all from me. Thank you.